For problem number 1 of homework chapter 15, it's asking to find the angular acceleration of p, which is this point right here. So we have this velocity and this velocity of these two different points. And then we know that the angular velocity is made up of these two components, and we have those. And then omega is this, alpha is this, and then we do the cross product of the two. And then I added an extra step just to show my work on this. You have the first one positive, then it's negative, then it's positive, and then you cross these two, you have this plus and then minus the multiplication or the product of those two, and they add it all together, and then I get a VP of this. And then the next part is to take that AP that we used and plug in the values that we know through the cross product. So it's the same process, and I got a final value of this. The next part, or the next problem, is asking for the angular velocity of b and angular acceleration of b. When we know the angular velocity and acceleration at a. So we have to use the law of sines to find these two lengths, because these are all known angles. And then, we get those lengths, then we use these unit vectors, and then we find the radius of PA, and we split that up into components. So we take the hypotenuse, we take the angle that it's at, and then get the into I and j components. We do the same for PB, and then this is a known, and then this is just saying that it's in the k direction. And then solving for angular acceleration, we have that that's known as well. So we go through, split this up into components again. Just algebra right here, and then we do the relative velocity and the relative acceleration using u dot, and then we also do, I guess, relative of p, or like the second position of p, and then we get a u of negative 9.9397 meters per second, a relative velocity of this, and then we use Coriolis acceleration. So you have this equation, and then we're able to break up the p prime acceleration into components again, and then we have angular acceleration bp equals 81.46 radians per second squared. For the next problem, we are solving for angular acceleration of a, b, and c along this, I guess, wheel with a rope around it. So the first step is to solve for velocity at b, which we can figure out by multiplying, or sorry, we already know the velocity at b, because it's the same as vd, but we want the angular acceleration. So we divide it by 2, which is 5 minus 3, which is the difference between these two. And then we get 4 radians per second, and it's not slipping. We get these different components going up up or down or left or right, so basically I and j. And then we get alpha equals 15 radians per second squared. Let's see, and then like a little lost on what I was doing. Oh yeah, and then we have that it equals 0, so then we can solve for what alpha g is, and then likewise for the rest of the components, there are the accelerations. And then the next problem, it's asking us to solve for angular acceleration at a and d. So here and here, and we have to find the angle between a, b, and c first. So this angle right here is beta, and then it ends up being 30 degrees. And we're given the rotations per minute, and then you can convert that into radians per second. Yeah, and then we have the velocity at b. We know that the angular velocity at AD is 0, and then we know that VA equals VB, which is 18.85. Yeah, and then at ABD, we have these different components. We can break it up into I and J, and then plug it back in and get the acceleration at A and D. The next problem is 3 different gears, and we are given the angular velocity of A, B, C, and B, and then we want to find the instantaneous centers of rotation of A and C, the angular velocities of A and angular velocities of C. So there are all these different diagrams to show how the different gears are interacting with each other. So we have, this is all of them together, how the forces are acting on the centers of the gears. And then through that we can find VA and VC. And then if we focus on B, we have at the edge of this gear right here, there's a 0.2 and then a 0.1, which is the end of this gear. So then we have V1 and V2 velocities. And then similarly at A, we are going off the center of the gear, but we instead have to go to an additional point I, A, and we have to figure out what the length to that is. But since we already know what V1 is, we can figure out what the angular velocity at A would be, since these are all knowns. And then, yeah, so it's 4 radians per second, and then the length is just VA over the angular velocity. Very similar at point C, we have, 2 knowns. We find the angular velocity, and then we find the length. So from those, the lengths, we figure out what the instantaneous centers are at A and C, and then again through those diagrams we can figure out the angular velocities at A and C as well. The next problem is 2 wheels connected together. There's no slipping. We have the lengths of AD, BE, and the initial velocity of D. We want to find VE, and we have that the angular velocity at D is VD over the radius of D to P, which is equal to 1 radian per second, and then we solve for VA, which is this, and then we focus on point E, which will be in the K direction, and then we separate it out into components, and then or the radius into components, and then we have that VB equals VBQ, which is, yeah, right there. And then AB, solve for that radius as well, and then we get the velocity. And then plugging it all back in together and separating it out into components, we get these two I and j components, and then we can solve for VE. Next problem is a system of, I guess, bars between two walls. And we want to find VA, VB. There's rotation happening at DE. And yeah, so we start off finding VD, which ends up being 288 millimeters per second. And then focusing on AD, B, I don't have B label, oh, right here, ADB, this bar right here. It's just, you know, adding those two lengths together, but since they're in component form, makes it a little more confusing. But we have that the velocity is VD plus the rotational yada yada yada, and then we can separate it again into components, and then we have the velocity at A. And then next we have to find the velocity at B. A similar process where you just add up these two velocities, and then BD equals this, and then you have the components, and then you can figure out what the angle of that hypotenuse is. The next problem is oh yeah, there's a bunch of different velocities at these different points along this wheel, and we have all of these given components, but we want to find the overall rotational acceleration and velocity at B. So for this one, we basically, what do? We find VBA, which is this, VCA, and then we have this equation for VB that we'll use later. We can separate that equation out into components, solve for the equation of VC, separate into components, and then from there we solve for the rotational velocity. Let's see, yeah, and then we solve for the velocity at B. This next problem has two sets of gears pulling a load 20 feet into the air, which is equal to 240 inches. We're given that it accelerates up to a constant speed of 120 rotations per minute in 5 seconds, starting from rest. We have the dimensions of the gears, and we want the number of revolutions to raise the load and the time to raise the load. So for the first part, we have to figure out how many radians it takes B to raise the load. So we know how many rotations per minute it's going. Or sorry, it's supposed to be in inches. Anyways, 240 over 15 is 16. And then we use this equation, this S, and this will give us the ability to figure out the radians for delta A. I need to come back to this because I'm not sure why this is 18. I mean, I know that it's 15 plus 3, but I need to figure out why it's assuming, I don't know. Anyways, need to come back to that. But delta A is 96 over 2 pi. To convert it into revolutions, it's 15.3. And then We have alpha is just the difference in the rotational velocity over time, and we have those, and it's 2.5 radians per second squared. And then theta A is 1/2 alpha t squared, which is 31.4 radians. And then delta theta is this, and then delta theta is the velocity times difference in time, and then we can solve for time, and it's 10.14 as the total time. The next problem is a system of gears and pulleys, or I guess one pulley, and these have different heights. So it's asking for the time for the rotational velocity to be 400 rotations per minute with belt in each position. So we're moving the I guess I don't know what these would be called, like the other radiuses or gears into position, getting different R values. So first we have to figure out what the rotational velocity at A is, as well as B, and then we can solve for T. Yeah, and then we can write T in terms of the radius, and then get these values. And that's it.